Alright, so last time we said that significant uncertainties have measurements in them, and the way we report measurements should reflect the level of uncertainty we have in those measurements. And in that context, we talked about significant figures. We say that the last significant figure should give you an indication of the level of uncertainty in your measurement. So here's a question. Which of the following is the fewest number of significant figures? 10.50, 20,700 milliliters, 0.003100, or 1.500 times 10 to the negative third. Well, correct answer is B. Okay, 10.50 has 4 significant figures. Okay, start with the first non-zero digit and go all the way to the end if you have a decimal point. So 1, 2, 3, 4. 20,700 has no decimal point, so you start with the first non-zero digit, you stop at the last non-zero integer. So that's 3 sig figs. 0.003100, so start with a 3 and go all the way to the end, that's 4 sig figs. And this one's written in scientific notation, so all the digits in the coefficients are sig figs, so that's 4 sig figs. So the correct answer is B. B is the correct answer. Fewest number of sig figs, in this case, 3. Here's another question. Let's say the amount of an acid in the sample was measured several times, and the average value was determined to be 3,601.2 milligrams, with an uncertainty of plus or minus 30 milligrams. To how many significant figures should the average be reported? Okay, so let's write 3601.2, and the uncertainty is plus or minus 30. The first non-zero digit in the uncertainty is in the tens place, right? So that's your tens place. So this is the ones place, that's the tens place. So this 0 right here is your last significant digit. There should only be, that should be the last significant digit. And the 3, the first non-zero digit, is your first significant digit, first significant figure. So from 3 all the way to 0, that's 3 significant digits. The correct answer is B. How about this one? The 5 replicate measurements of the calcium content of a sample, and you got the following results: 5.042%, 5.131%, 5.434, 4.852, and 4.728%. So how many significant digits should we report the average? Well, let's take a look at these numbers. To determine how to report the average, you estimate the uncertainty, and the quickest way is to just determine half the range. Okay, so the range is the highest. This is the highest number here, 5.434, and the lowest here is 4.728. So that's about the difference is the range. That's 0.7 approximately. Okay, so half the range uncertainty is approximately about 0.3, 0.35, or 0.4. That means whatever your average is, let's look at these numbers. What would be your average here? It's going to be 5 point something or 4 point something, right? And since you're already starting to have doubts in the tenths place, the first decimal place, that's as far as you should go. So you should only be writing 2 significant digits when you report the average of these measurements. So the correct answer here is 2 significant digits. How about this one? What's the proper way of reporting the temperature shown in the scale below? 30, 30.0, 30.00, or 3.0 times 10 to the 1. Let's see. The adjacent marks are separated by how much? let's see, this is 30, this is 31. There are 10 marks in between, so this is 30.1, 30.2, 30.3, 30.4, 30.5. So adjacent marks are 0.1 degrees apart, and you should be able to guess one decimal place beyond that. So if you are going to use this scale, okay, the uncertainty should be at least around a tenth of 0.1, so 0.01. So you should be able to report any measurement from this scale to the nearest hundredth, to the second decimal place. So the correct answer is 30.00. It looks like it's spot on at 30, but there's an uncertainty associated there. So to report it properly, you should say 30.00. Okay. Now, when calculating with units, we treat units just like any algebraic quantity. You have to remember that anytime you put a number in front of a unit, multiplication is implied. So if you say 5 kilograms, that's the same thing as 5 times kilograms, just like you would say 5x in algebra is 5 times x. So when adding or subtracting quantities that have units, the units have to be the same before you can combine the numbers. Okay, just like if you do 5x and 2x, you get 7x, right? So you can treat x as a variable, kilograms as a variable, just like x. So if you have 5 kilograms plus 2 kilograms, that's going to give you 7 kilograms. So distributive property right here, you can factor out your kilograms. So you have 5 plus 2, and so that gives you 7 kilograms. Now, what happens if you multiply, divide, or raise an exponent? Well, like I said, just treat it just like any algebraic quantity. So if you have something like 2 meters times 3 meters, okay, 2 times 3 is 6. Meters times meters is meters squared. So that's 6 meters squared. It's just like you would say 2x times 3x in algebra. You'd say 2x times 3x is 6x squared. Okay. What you can also multiply or divide. So what happens if you divide? You have 6 meters in this example divided by 2 seconds. This would be like calculation for speed. That would be the same thing as 6 divided by 2 is 3, so that's 3 meters over seconds. So you say 3 meters per second, so that's what that slash means. Or you can say, if you remember from algebra, 1 over x is the same thing as x to the negative 1 power. So this is 3 meters times reciprocal seconds, or inverse seconds. So you can write meters per second that way. Meters times seconds to the negative 1 power. What about, okay, so when you are using measurements in calculations, okay, there's uncertainties in your measurements, you would expect the answer to have uncertainties as well. So the way you express your answer should reflect the uncertainty in the numbers that you use to get to that number. So the rule is, if you're adding or subtracting, you round off your answer to the same number of decimal places as the least precise term. And the term that is least precise, or the less precise term, if you're just adding 2, is the one that has the largest uncertainty. So for example, let's see what happens if you add 25.0 grams and 1.003 grams. Well, 25.0, the uncertainty there is in the tenths place. So the uncertainty is at least 0.1 gram. In 1.003, the last significant digit is in the thousandths place, a third decimal place. So the uncertainty is at least 0.001 gram. 1 unit in the last decimal place, the last significant digits, decimal place. So which term is less precise? The 25.0 is less precise. So we should round off our answer to the same number of decimal places as 25.0. In this case, to the first decimal place. So if we were to do this, you would say 25.0 grams plus 1.003 grams is 25.003 grams. Okay? 25, the last decimal place of 25.0 determines how far you round off your answer. So, oops, the answer is 26.003. So, the answer should be reported as 26.0 grams. Let's try this one. You'll notice you're adding two things and then subtracting the other one. All right, and you'll notice that these are all written in scientific notation. So you cannot just add this in your calculator and figure out from there how to round off. The best thing to do in this case is to change all of these numbers so that they have the same exponent, the same power of 10. So a good strategy is to keep the largest power of 10. So -3, -4, and -5. Of the three, -3 is the largest. So the first number, you keep it as 4.2 times 10 to the -3rd. The second one, 4.4 times 10 to the -4, you change it to an expression that says something times 10 to the -3rd. Well, let's see. If this number is to remain the same, I made my power of 10, I made that larger, right? So I have to make my 4.4 smaller. So how do I make 4.4 smaller? I went up, I made this larger by a factor of 10. So to make this smaller by a factor of 10, I move the decimal point one place to the left. So this becomes 0.44. So this is 0.44 times 10 to the -3rd. And so the third term there is -3.5 times 10 to the -5. So let's change that. 3.50 times 10 to the -5. So change that to something times 10 to the -3rd. From 10 to the -5 to 10 to the -3rd, you made it larger by 10 by 100, right? So that means you have to make this coefficient here smaller by 100, so you move your decimal point 2 places to the left. So this is going to be 0.0350. So now you have all your numbers with the same power of 10. You can apply the rules now for addition, rounding with sig fig. So 0.0350 times 10 to the -3rd. So let's have all of those numbers now in one place. You have 4.2, 0.44, and minus 0.0350. Okay. So if you did that, let's see, let me pull up a calculator here. 4.2 plus 0.44 minus 0.0350, that's 4.605. All right, and you can see here that the least precise term is this one right here, 4.2, so you should round off your answer to 4.6. So the answer here is going to be 4.6 times 10 to the -3rd. What if you're doing multiplication and division? The rule for this is you round off the answer to the same number of sig figs as the least precise term. Okay, and the least precise term for purposes of multiplication and division is the one that has the fewest number of significant figures. Now the justification for this is in calculus, so we can't go into that at this level. We're just gonna have to accept this rule. All right, so 16.00, for example, 16.00 grams divided by 2.00 mils. So we're doing division, so we count sig figs. 16.00 grams has 4 sig figs, and 2.00 has 3 sig figs. So the less precise term is 2.00, so our answer should have only 3 sig figs. So 16.00 divided by 2 is 8, so that's 8 grams per mil. But we should not report that simply as 8 grams per mil. We should report it to 3 significant digits. So how do we make this 3 sig figs? You write it as 8.00 grams per mil. That gives you 3 significant digits in the answer. But if you have to do multiple operations, then it's useful to just do it step by step, and you apply the rules for rounding in each step. But you have a tendency to build up round-off errors if you round off to the correct number of sig figs for each step. So it's best to keep an extra digit in the intermediate steps. Just make sure you keep track of what the last significant digit is in each step. Okay, so for example, if I did 25.1 times 1.0, the answer there is going to be 25.1. Okay, I do this multiplication first. That's 3 sig figs. This is 2 sig figs. So my answer should only have 2 sig figs. So 25.1, the 5 here is the last sig fig. I'm going to mark that, but I'm not going to drop that 1 just to be safe, okay? So I don't build up round-off error. So now I proceed to the next step. I have 25.1 plus 2.5, keeping in mind that this 5 right here is my last sig fig, and of course in 2.5 this is my last sig fig, the 5 right here. So if I add the 2, I get 27.6, and based on the rule for addition and subtraction, that units place, the ones place, is my last sig fig, since my uncertainty in my 25.1 is at least 1 unit there. So 27.6 should be rounded off to 28. Now, the idea of significant figures applies only when we're dealing with numbers that have uncertainties or measurements. The last significant digit indicates the level of our uncertainty. Now, there are some numbers that, by definition, they just don't have any uncertainty. So, for example, if I say I have 10 fingers, okay, there is no uncertainty in that 10. I'm not saying it's either I can be off by 1 or 2. I know exactly that I have 10 fingers. So that 10 is what we would call an exact number. You can write it as 10.00000000. You'll never get to a point where you have to have any doubts about that number. So we say, for purposes of doing calculations, an exact number is one that has an infinite number of significant digits. So it can never be the least precise term in your calculation. So in any calculation you're doing, it can't be less precise than any other number. All right, so besides small counting numbers, what's another example of an exact number? Numbers that are used in defining the relationships between units are generally defined to be exact. So when you say, for example, when you define an inch to be exactly 2.54 centimeters, that's a definition. In this context, the number 1 and the number 2.54 are defined to be exact. So the number of significant digits in 1 and 2.54 in this particular context is exact, is infinite. Okay, the numbers are exact. The number of significant figures is infinite. Now, if I said I made a measurement of 2.54 centimeters, then that's 3 sig figs. Okay, so you have to know the context by which you're using a number. If you're using it because in the context of the relationship between an inch and centimeter, then the number 2.54 is exact. If you're using it, if you're saying you have 2.54 centimeters in the context that you actually measured something that's 2.54 centimeters, then you're looking at 3 significant digits there. Let's look at an example. Let's say you have the following formula. This is actually the formula you would use to convert a temperature reading in Celsius to Fahrenheit. Okay? In this formula, by definition, the relationship between Celsius and Fahrenheit is defined this way. Whatever the Celsius reading is, you multiply by 1.8, and then you add 32 to get the Fahrenheit reading. In this context, the numbers 1.8 and 32 are exact. So what if C happens to be 20.0? How are you going to calculate F? Well, let's see. 20.0 times 1.8, that gives us 36. Okay. Now, 20.0 has 3 sig figs, and 1.8 has 2 sig figs. So your final answer here should, I'm sorry, 1.8 is exact. So has an infinite number of sig figs. So this 36 right here should have 3 sig figs. So I should write it as 36.0. Okay. This is an intermediate step. I can add an extra digit, but the extra digit is going to be 0 anyway, so I'll just leave it at that. Now I add 32 to that. 36.0 plus 32. So this is my last sig fig in 36.0. Remember, when you're adding or subtracting, you keep track of the last significant digit, the decimal place for it. Now 32, by definition, in this context, is an exact number. So this is really 32.000000000. Okay, so when you add these two numbers, you get 68.0, and it's a 36.0 that determines how far you should go. So that's 68.0. So if you're in a room that's at 20 degrees Celsius, it's a nice comfortable room at 68 degrees Fahrenheit. The final answer here is 68.0. Now, when a number is very precisely known, then you can run it off as long as you're not making it less precise than any of the other numbers in the calculation. So for example, speed of light is defined to be exactly this number, 2.99792,458 times 10 to the 8 meters per second. Now if you have to use that, okay, number in a calculation, you don't have to use all the digits if it's not necessary. Okay, for example, let's say you want to plug that into Einstein's equation, E equals mc squared. Well, your mass is let's say your mass is only known to 3 significant digits, so that's 10.0 kilogram in this example. Well, you don't have to put all the digits for C in here, because you know you're going to round off your answer to 3 sig figs anyway. So in this case, you can save yourself some time and trouble by just rounding this off to 4 sig figs. Okay, so instead of 2.99792,458, you can round out to 4 sig figs. So that's going to be 2.998 times 10 to the 8. So you say this is times 2.998 times 10 to the 8 meters per second. Okay. What if you're dealing with logarithms? Sometime later this semester, when we calculate pH, we'll be using logarithms. The rule for logarithms is this: the number of decimal places in the result should be the same as the number of significant digits in the coefficient of the number as written in scientific notation. So for example, let's say you want to take the log of 2.7 times 10 to the 4th. Okay, so that's 2.7 times 10 to the 4th. That has 2 sig figs, right? If you're going to take the log of that, your answer should have 2 decimal places. So if we did this on your calculator, what do you get? So you would type in 2.7 times 10 to the 4th. Okay, and take the log, base 10 log. The calculator gives you 4.43136, 4.4314. But since this has only 2 significant digits, your answer should only have 2 decimal places. So the answer here is going to be 4.43. All right. What if, let's say, you had 2.7 times 10 to the, let's say you want to take log of, let's use the same number but with a different exponent, 2.7 times 10 to the 14. Okay, you'll find that if you did this, you're going to get 14.4314. So again, here you have 2 significant digits in the number that you're taking the log of, then your answer should have 2 decimal places. So your answer here is going to be written as 14.43. Alright. Now, what if we did the reverse? We were to take the antilog. So if you were to do the reverse, then the number of decimal places in the number you're starting with should be the same as the number of significant figures in the answer. So here, the antilog of negative 2.699. Okay, so you're taking the antilog. You look at how many decimal places you have. You have 3 decimal places. So if you have to take the antilog of 2.699 to 2.699, the answer should have 3 sig figs. So you have 3 decimal places. Your answer should have 3 sig figs. So let's do that. Negative 2.699. Oops, I'm sorry. Clear. Negative 2.699. Negative. Inverse log is this 10 to the x right here. Okay. So that gives you what's that? 0.00199998. 3 9s and an 8. Okay. That's 3 sig figs. That means this is the first non-zero digit. That's your first sig fig. 1, 2, 3. You round off there. And so your answer is going to be, so if you round that off, that gives you 0.00200, or 2.00 times 10 to the negative third. That is how you would determine the antilog. Okay, here's a few clicker questions. A few questions you can use to test yourself. To how many significant figures should the result of the following calculation be reported? 2500.0 plus 25 grams. So this is addition. The rule we follow is we look at the decimal place, the last decimal place, in the least precise term. So 2500 plus or minus 2500.0, the uncertainty here is at least plus or minus 0.1. In 25 grams, the uncertainty is at least plus or minus 1 gram. So this ones place is where we round off our answer to. If you add these two, you get 25.0. Since ones place is our last significant digit for the less precise term, that should also be the last significant digit for our answer. So the answer is 2525. We drop that 0. The answer here would be 4 significant digits. How about this one? To how many significant figures should the result of the following calculation be reported? 2500 mils. That's 2 sig figs. And 25 mils. That's also 2 sig figs. But since we're doing addition, we go by the decimal place of the last sig fig. So the last sig fig in 2500 is this 5 right here in the hundreds place. That means you can be off by at least 100 there. Okay. And the last sig fig in 25 is in the ones place. This can be off by at least a mil in the ones place. So the answer, 25 milliliters. You go by the last sig fig. It should be in the hundreds place. You should be rounding it up to the nearest 100. And so this should be rounded up to 2500 milliliters. And so there's only 2 sig figs. The answer is A. Now it might bother you that you're adding 2500 and 25 together and you're still getting 2500. Think of it as a drop in a bucket. Okay? When you say 2,500, what you're saying is you can be off by as much as 100 already. So what's the point? What's the difference? But if you add 25 more, it's not going to make much of a difference. So you still be uncertain by at least 100. So the answer should still be 2,500. Let's apply the rule for multiplication and division. Here we're dividing 80.00 grams divided by 10.0 mils. In this case, since we're dividing, we have to apply the rule for multiplication and division. And in that case, we count sig figs. 80.00 grams has 4 sig figs. And 10.0 mils has 3 sig figs. So the answer should have 3 sig figs. The fewer number of sig figs. So 80 divided by 10 is 8, right? But it should be reported to 3 sig figs, so you should write it as 8.00, and don't forget the units here, it's grams per mil. Correct answer in this case is C. How about this one? 0.800 meters divided by 0.010 seconds. Let's take a look at this first number. Again, this is division, so the rule is you count sig figs, and the answer should have the same number of sig figs as the factor that has the fewer sig figs. So this has 3 sig figs. This one doesn't have 3 sig figs, it only has 2. The first significant digit is this one right here, so 1, 2. That's 2 sig figs. So the answer here should have 2 sig figs. So 0.8 divided by 0.01 should give you 80, but you need 2 sig figs. How are you going to write 80 with just 2 sig figs? If you write it like that, that's only 1 sig fig. You can write it as 80 point, okay, which is not one of the choices given here. 80.0 is 3 sig figs, so this is not right. A is not right, and 8 times 10 to the 1 is just 1 sig fig, so that's not right either. 8.0 times 10 to the 1 is 80, so the correct answer here is C, 2 sig figs. Let's do this multi-step calculation. How should we round up the answer? Well, let's do the multiplication first. According to this, treat the numbers 1.8 and 32 as exact. So 2.37 has 3 sig figs. Multiplied by 1.8, this is an exact number, so you have an infinite number of sig figs. So the answer should have only 3 sig figs. And if you did this, let's see, 1.8 times 2.37, that gives you 4.266. This should only have 3 sig figs, so 1, 2, 3. So this 6 right here is my last sig fig, okay? And that extra 6 there, I just keep that because this is an intermediate step. I don't want to build up round-off errors. So if I add that to 32, 4.266, keeping in mind that this is my last sig fig here, the 6, the first 6, plus 32, which is exact. That means since it's exact, I can write it as 32.00000000. Final answer would be 36.266, but I have to round off to same number of decimal places as the less precise term. This is in the hundredths place, the second decimal place. This should be rounded up as 36.27. Correct answer is C. What about this problem right here? Volume of a sphere, a radius r is given as 4/3 pi r cubed. The radius of the sphere is 5.00 centimeters. What's the proper way to report the volume? Well, here's pi. It's 3.141592653 and so on. So how far should you round off your pi? You should, since your r is given to 3 significant digits. Okay, by the way, 4 and 3 here in this formula are exact. So the only term here that has an uncertainty is r, and it's given as 5.00 centimeters. So you have 3 significant figures. So your answer should have 3 significant figures. So right away here you can rule out choice A. That's only got 2 sig figs. Question is, what number should you get? Would you get 523 or 524? Well, it would depend on how you round off your pi. What's the best way to round off pi? If you have 3 sig figs in your least precise term, then you cannot round off pi to fewer than 4 sig figs. So maybe you should keep 3.142, or you can keep it as 3.1, express as a 3.1416. Or if your calculator gives you more digits, then that's fine too. So let's do that on your calculator. Oops. Where's the calculator? There's pi. If I do 3.14, okay, let me take 5 cubed. 5 times 5 times 5 equals 125 times 3.14. That would give me, okay, times 4/3, so times 4 divided by 3. That gives me 523.33. So if I were to use 3.14 for my pi, 3 sig figs, that's the number I get. If I use 3.142, the number I would get would be, let's see, 5 times 5 times 5 times 3.142 times 4 divided by 3. That gives me 523.6. 6666. So you can see, what if I were to use 3.1416 for my pi? I would have, okay, 5 times 5 times 5 is 125 times pi 3.1416, oops, times 4 divided by 3. That's 523.6. You'll notice, okay, the best answer here is 524. Okay, 523.6. And since we have to keep only 3 sig figs, then your answer here would be 524. The best answer is C. All right. And try to do this at home. This will be our first clicker question for the next lecture.